Okay, so let's talk about this term effusion. Effusion is like diffusion. If I have a gas in a container and I open the lid, that gas is going to diffuse. It's going to move out and spread apart. Effusion is similar to that, but what I have here is I make a little hole, and that hole is a spot where particles, if they have the right orientation and the right speed, will come out. Okay, so we're going to be looking at what's the rate of effusion. Alright, so we can look at, for instance, the difference of the rates of effusion for helium and nitrogen. And as you would imagine, the nitrogen is a bigger molecule, so it is going to effuse more slowly than a helium would. Okay? So a helium is, if I filled two balloons, one with helium and one with nitrogen, the one with helium is going to deflate faster because it's going to come out these tiny little gaps that are in the balloon. So we said diffusion is the spreading of a substance throughout a space, right? So Graham's law allows us to compare the effusion of one gas to another. So for the first gas, kinetic energy is going to be 1/2 mv squared. For the second gas, energy is going to be 1/2 mv squared. So if I solve, rearrange this, I get the mass of one over the mass of the other is equal to the velocity squared of one over the velocity squared of the other. Okay, so don't forget I got gas 1 here and gas 2 here. They invert when I get to the molar mass on this side. Okay, so here's the Graham's law. Get a question on the multiple choice though, so you've got to understand conceptually that the bigger the molar mass, the more slowly it will effuse. Alright, so an unknown gas compound of a homonuclear diatomic molecule, which means it's something like H2 or O2, effuses at a rate only 0.355 times that of oxygen at the same temperature. Alright, and calculate the molar mass of the unknown and identify it. Okay, so what I know is the rate of some gas over the rate of oxygen is 0.355. Okay, so it's 0.355, and I know that it's equal to the square root of the molar mass of oxygen over the square root of the molar mass of this gas. So let's just rearrange the equation first because I want to solve for the molar mass of the gas. So 0.355, actually let's do this. In order to solve for this, I got to square everything. Square this, square this, square this. So I end up with 0.355 times the molar mass of the gas is equal to the molar mass of oxygen. So when I square this, I just get rid of this square root, right? So my molar mass of my gas is going to be my molar mass of oxygen divided by, this should be squared, 0.355 squared. So I know my molar mass of oxygen is 32, right? And if I put that over 0.355 squared, let's see what we get. Alright, so I have 32 divide by, I'm going to put in parentheses, 0.355 x squared, close my parentheses, and I get 253. Now this is going to be 0.9 grams per mole. Okay, so what I know is this is a diatomic gas. It told me here that in the problem. So I got to divide this. If I divide this by 2, I get about 127 grams per mole. And if I look at the periodic table, well, that matches up quite nicely with iodine, which has a molar mass of 126.9. So the gas in question is I2.